Still within confidentiality as the classic security goal of cryptography, we have reached asymmetric encryption. Again, going now into the topic of asymmetric encryption, remind yourselves of the approach from the analog world we got to know that makes use of mailboxes to provide confidentiality to plain text exchanged. Asymmetric encryption as the key property and also main difference to symmetric encryption now makes use of a pair of keys made up of a public key and a corresponding private key. The public key is the key that is used for the encryption of a plain text into a ciphertext, and the private key is the key that is used for the decryption of the ciphertext back into the original plain text. Looking at the flow chart for the asymmetric encryption on the left side of the slide, we can see that in order to encrypt a plain text, we need to get hold of the public key of an asymmetric public-private key pair, and it's then with this public key that we can encrypt the plain text into the ciphertext. This ciphertext looks to anyone without knowledge about the private key like a random piece of data. However, the owner of the private key associated with the public key used for the encryption can then use this private key to decrypt the ciphertext back into the original plaintext. The questions that we have left to answer are: how do the encryption and decryption processes now work within asymmetric encryption systems? What is really the relationship between an asymmetric public key and its corresponding private key? And what is the notion of security associated with asymmetric encryption processes? An absolutely quintessential asymmetric encryption scheme is RSA. RSA stands for Rivest, Shamir, and Adelman, which are the names of a computer scientist and two mathematicians who, back in 1977, published the asymmetric encryption scheme that we are about to get to know now. The scenario to help us walk through the inner workings of RSA is to have an Alice and a Bob, where Alice is the one that wants to be able to receive confidential data, for example, then being sent by Bob. In the analog example with mailboxes, the setup to achieve this would require Alice to own a mailbox together with having access to the private key of the mailbox, and with Bob then ultimately posting his data or plaintext into Alice's mailbox. Alice would then recover Bob's plaintext by making use of her private key of the mailbox. With RSA, the setup now requires for Alice to own a public-private RSA key pair, with the public key of Alice then being made public, such that Bob can retrieve an authenticated copy of this public key of Alice. In the drawing, I simplified this by just providing a registry of public keys. This is of course very simplified, and in reality, authenticated copies of public keys could, for example, be provided by making use of X509 public key infrastructures. If we now assume that Alice generated such a public-private key pair and published this public key into a public registry of keys, then conceptually speaking, Bob can now retrieve the public key of Alice from this registry of keys, and with this public key of Alice can then asymmetrically encrypt the plaintext that Bob wants to confidentially send to Alice. Once Bob encrypted the plaintext into the ciphertext like this, Bob sends the resulting ciphertext to Alice, who, by making use of her private key, can then recover the original plaintext from the ciphertext. In the next couple of slides, we will have a look at the actual steps that need to be performed by both Alice and Bob in order to pull this RSA-based asymmetric encryption and decryption of a plaintext really off. First, and in order for Alice to participate in a RSA-based asymmetric encryption system, Alice needs to own a public-private RSA key pair. In order to create such a public-private RSA key pair, Alice needs to generate two large prime numbers, which we will denote as P and Q. Prime numbers are numbers larger than 1, which are only divisible by 1 and by itself. So, for example, 2, 3, 5, 7, 11, 13, and so forth. It turns out that generating large prime numbers is actually not that straightforward, especially when the prime numbers involved are large. Nowadays, it's recommended for RSA key pairs to be of length at least 2048 bits. For a 2048-bit RSA key, the prime numbers P and Q that Alice needs to generate are both each 1024-bit prime numbers. Finding prime numbers of that size is then done by following the process described on the left side of the slide. In order to choose a large prime number, Alice first draws a completely random odd number P of the required size, so for example 1024 bits. Then Alice goes on to test if this randomly sampled number P really is a prime number. If this is the case, Alice chooses number P as one of her prime numbers. If the test is negative, meaning that the random number P is not a prime number, then Alice simply draws a new random odd number of the required size and repeats this process until a random odd number is a prime number. Well, in reality, it's of course not Alice that executes this process with a pen and paper, but a piece of software, and the primality check is often a primality check now known as Miller-Rabin primality test. This Miller-Rabin primality test is very efficient even for large numbers, but it is a probabilistic test with a false positive rate of 1/4. This means that if asking whether the number P is prime returns yes, then this yes is wrong in 25% of the cases. What's now done by libraries such as OpenSSL is to just ask this question whether P is prime a couple of times in a row and only conclude that P is prime if the answer to all of these questions was yes. This allows to bring the false positive rate down to an arbitrarily small probability, and libraries such as OpenSSL often ask that question 64 times, which brings the false positive probability down to 1/2 to the power of 128, and thus gives us a security of the number P then really being prime in the same order as AES delivers security to a ciphertext when using 128-bit AES keys. As all the involved processes and algorithms are very efficient, even for large numbers involved, the generation of two large numbers can be done very efficiently by Alice. Once Alice generated her two prime numbers of at least size 1024 bits each, then Alice can use these two prime numbers P and Q to calculate her public key. The public key is a pair of numbers n and e, where n is simply the product of these two prime numbers P and Q, and where e is a number that's relatively prime to the product P minus 1 times Q minus 1, and with e in practice often actually just being set to the number 2 to the power of 16 plus 1. The condition on e to be relatively prime to P minus 1 and Q minus 1 guarantees the existence of a corresponding private key. Calculating this public key is efficient even for very large prime numbers, as fast algorithms exist for multiplication, and as such, calculating the public key of Alice is a very efficient process. Once Alice calculated her public key, she can proceed to calculate the corresponding private key. The private key is again just a number called d, but this number d needs to be such that d is the multiplicative inverse of the public exponent e. This property is essential that later on the decryption process can undo the encryption process, as we will see later on. Calculating such a d can be done very efficiently by Alice, who knows her two private prime numbers P and Q, and for which she can use the extended Euclidean algorithm. On the other hand, no efficient algorithms are known to calculate the private key D if the prime numbers P and Q are not known. Realizing that the public key of Alice has the prime numbers P and Q embedded in the modulus N, which is simply the product of P and Q, RSA then fundamentally relies on the assumption that factoring a product like N back into its prime numbers is difficult. This is an unproven assumption known as the integer factorization problem, and up until today, no efficient algorithm is known to factor a product back into its prime numbers if the prime numbers involved are of a sufficiently large size, like for example 1024 bits each. Now that Alice has her public-private key pair generated and has made her public key available by publishing it, for example, in the public registry of public keys, Bob, who now wants to confidentially send a plaintext P to Alice, encrypts this plaintext P simply by just calculating P to the power of E modulo N, where E and N are the numbers of Alice's public key. This calculation of P to the power of E modulo N is efficient even for large numbers E, such as 2 to the power of 16 plus 1, and as such, this encryption process of a plaintext into a ciphertext can be done very efficiently by Bob. Bob then sends the result of this power to the E calculation as a ciphertext to Alice. Alice, who now receives a ciphertext from Bob, can recover the plaintext by making use of her private key and by simply calculating the received ciphertext to the power of D, her private key. This calculation of the ciphertext to the power of D, her private key, results, if we look at the arithmetics, in a calculation of the power of the plaintext to the product of E and D, which, due to the choice of D, her private key, we know to be ultimately 1. This arithmetics shown here on this slide is simplified, but it allows us to see the basic ideas. From this, it's clear that by simply calculating the ciphertext to the power of her private key D, Alice can recover the plaintext originally sent by Bob. And moreover, this process is very efficient for Alice, even if the number D involved is very large. This is RSA. We have seen how RSA, at least the textbook version shown on this slide, is a very efficient encryption system for all the parties involved, and how RSA ultimately relies on the assumption of the integer factorization problem to be a very hard problem. We have so far repeatedly pointed out that symmetric encryption systems, the safe-like approach living within cryptography, doesn't scale well in terms of the numbers of keys required to provide confidentiality to a group of participants. For example, we have seen that with symmetric encryption, a group of just 5 participants requires 10 keys to be established. With asymmetric encryption systems such as RSA, the only requirement is that each participant owns a public and private key pair. From this, we see that instead of the 10 keys, like in symmetric encryption systems, with asymmetric encryption systems, only 5 key pairs are required for a group of 5 participants. Generalizing this, we see that the numbers of keys required for n participant is just n key pairs, which is a number of key pairs that scales perfectly well with the numbers of participants in the system. This allows us to conclude that at least in terms of the numbers of keys required, asymmetric encryption schemes are more efficient than symmetric encryption schemes. The efficiency of symmetric and asymmetric encryption schemes can not only be compared in terms of the numbers of keys to be used, but also, for example, in terms of the length of the keys involved, the size of the plaintext that can be encrypted with the invocation of exactly one encryption operation, as well as, of course, the general speed with which encryptions can be calculated. In terms of the numbers of keys involved, we already know that asymmetric encryption systems manage to outperform symmetric encryption systems, which I have indicated in this table by coloring the asymmetric encryption scheme as green to indicate an outperformance of asymmetric encryption over symmetric encryption in this regard. Looking at the length of the keys involved, we know that the keys used with AES are either of length 128 bits, 192 bits, or 256 bits. For RSA, we know that nowadays RSA keys need to be at least of length 2048 bits, preferably even 4096 bits. In that sense, as longer keys mean more storage requirements, symmetric encryption schemes seem to outperform asymmetric encryption schemes. Looking at the block size, we know that AES just purely by itself encrypts plaintext blocks of length 128 bits. RSA, on the other hand, can encrypt plaintext with lengths just about the length of the RSA keys involved. So for example, if we have a 2048-bit RSA key, then RSA can encrypt just about 2048-bit plaintext. From this, we can see that the block size of asymmetric encryption outperforms symmetric encryption schemes by almost one order of magnitude at least. Last, looking at the speed with which the encryption schemes manage to encrypt data, performance measurements with, for example, the built-in OpenSSL speed test are allowed to conclude that symmetric encryption schemes with AES are roughly 200 times faster than asymmetric encryption schemes based on RSA. Among the factors contributing to this is that AES was, among others, chosen as the new standard due to its design, allowing for highly efficient implementations, with nowadays most of the CPUs having dedicated instructions to execute AES. Taking a step back and looking at the coloring of the table, we see a chessboard-like pattern clearly indicating that each encryption approach has strengths and weaknesses, a fact that we have already observed in the introduction when we talked about approaches to confidentiality in the analog world making use of safes and mailboxes. As we have done in the analog world with safes and mailboxes, where we combined the approach to combine the best of the two worlds, the same is done in cryptography, where the best of the two worlds of symmetric and asymmetric encryption schemes are combined into hybrid encryption schemes.